Hello everyone, my name is Stephen Benny. Today I'm going to be presenting about the optimization of Tokamak blanket design to minimize neutron flux. Once again, my name is Stephen Benny, and my mentor is Ms. Soha Asa. So for a bit of background about me, as a high school student deeply passionate about science and engineering, I've taken a particular interest into various aspects of nuclear fusion really, particularly focusing on nuclear fusion reactors. My curiosity in this field kind of stems from a desire to dive deeper into how we can contribute to sustainable energy solutions for our planet and kind of address the challenges of current energy production methods. I'm really fortunate to have Ms. Soha Aslam as my mentor throughout this journey. She's a distinguished nuclear physicist and engineer whose invaluable guidance and expertise have been instrumental in shaping my understanding and approach towards fusion research. Soha's mentorship has not only enriched my knowledge, but has also inspired me to pursue perhaps a career as a nuclear physicist in the future. Firstly, let's explore what tokamak reactors are and their key components in order to understand the objective of this research. Tokamaks are a type of magnetic confinement fusion device designed to contain and control plasma, the superheated state of matter where fusion reactions occur. Essentially, tokamaks are a type of nuclear fusion reactor, and the main function is that it uses magnets to contain and control plasma, which is where nuclear reactions happen and are essentially taking place. So central to the tokamak design are components such as the plasma chamber, magnets for confinement of the plasma, and the blanket. Now, the blanket is what this research project is mostly focused on. In a tokamak reactor, the blanket serves as a critical role as a protective barrier surrounding the plasma. It acts as a shield, absorbing excess heat and capturing neutrons produced during the fusion reaction. But why are neutrons so significant in blanket design? Neutrons, as byproducts of fusion reactions, carry a considerable amount of energy. This energy can cause structural damage to reactor components and cause even radiation hazards. Therefore, managing neutron flux, the flow of neutrons within this blanket, is essential in ensuring the safety and efficiency of tokamak reactors. So that brings us to our main point, minimizing neutron flux in tokamak reactors. So, as I've already said, neutron flux plays a pivotal role in the performance and safety of fusion reactors. By strategically optimizing the blanket design, we can mitigate potential risks while maximizing energy output. For example, safety concerns are are paramount when we come to discuss about nuclear fusion reactors. The blanket, as I've already said, acts as a shield between the plasma and the reactor walls, and it plays a crucial role in controlling the fusion reaction and extracting energy efficiently. Secondly, optimizing neutron flux is vital for the efficiency of energy production. Neutrons carry a significant portion of the energy generated in a fusion reaction. Therefore, by reducing neutron flux, we can maximize the energy extracted from the reactor, ultimately improving its overall efficiency and economic viability. Let's also not forget about the impact on neutron flux on materials. Neutrons can cause structural changes and degradation in reactor materials over time. By minimizing neutron flux, we can prolong the lifespan of reactor components and the nuclear reactor itself, reducing maintenance costs and enhancing the sustainability of fusion energy. So, in particular today, we're going to talk about the HCLL blanket design. The HCLL blanket design stands for the helium-cooled lead-lithium blanket. The helium-cooled lead-lithium blanket design represents a promising approach in fusion reactor technology and consists of a dual coolant system where liquid lead-lithium alloy serves as a breeder for tritium and neutron multiplier, while helium functions as the coolant. So helium basically serves to cool down the blanket as temperatures inside the neutron reactor can get extremely hot. What makes this blanket design particularly advantageous is its suitability for tokamak reactors. The use of helium as a coolant ensures efficient heat transfer, allowing for effective cooling of the blanket while maintaining stable operation of the fusion reactor. Additionally, the presence of liquid lead lithium lead alloy enables effective neutron multiplication and breeding of tritium, which is a very crucial fuel for fusion reactions. Now, let's discuss the role of the HCl blanket in neutron flux reduction compared to other blanket designs. The unique combination of liquid lead lithium lead alloy and helium in the blanket offers superior neutron capture abilities. This results in a significant reduction in neutron flux within the blanket compared to alternative designs such as solid breeder blankets. By minimizing neutron flux, the HCl blanket contributes to enhanced safety and efficiency of tokamak reactors. So, our approach begins with the utilization of OpenMC, a powerful Monte Carlo particle transport code for simulation. OpenMC allows us to model the complex interactions of particles, including neutrons, within the fusion reactor environment with high fidelity. In terms of the simulation process, it involved several key steps. First, there was the creation of a DAG-MC geometry, as in order to use OpenMC, I needed to test it on the helium-cooled lithium-lead reactor, which I was able to create using the software Fusion 360, and I was able to 3D model what you're seeing on the screen right now. So firstly, we constructed a detailed computational model of the fusion reactor incorporating the geometry of the tokamak, blanket design, and other relevant components. Next, we define the material properties and operating conditions to accurately represent real-world scenarios, to the best of my ability at least. Once this was complete, I was able to execute Monte Carlo simulations to study the behavior of neutrons within these blankets under various conditions. The simulations would hope to provide valuable insights into the neutron flux distribution, perhaps even the heat deposition patterns and other important parameters when we're trying to solve this problem, or look at what would make this helium-cooled lithium-lead blanket very effective. Now, let's talk about the parameters considered for optimization. Our study encompassed a wide range of factors, including blanket thickness, composition of the breeder material. We even considered coolant flow rates, even though that was a particularly hard challenge to do, as it would be very tough to model. By systematically varying these parameters, essentially, and analyzing their effects on neutron flux reduction, we aim to identify optimal configurations that maximize safety and efficiency. So, through this optimization sort of process and playing around with the parameters, I was able to come up with some initial results. These results are not concrete, as simulation of this material would actually take a lot more time than the Polygence project has permitted, as this project was actually at a much bigger scope than I initially foresaw. So there's a lot of work to still be done, but here are some of the initial results that I was able to gather. Firstly, altering the thickness of the blanket material exhibited a notable impact on neutron flux. Increasing the thickness led to a considerable reduction in neutron flux penetrating through the blanket layers. This shows how the blanket's enhanced shielding capability with thicker material effectively minimized the influx of neutrons into the surrounding components. Moreover, I also played around with different material compositions, which produced some interesting insights. Utilizing materials with higher neutron absorption cross sections demonstrated a pronounced decrease in neutron flux throughout the blanket volume. This kind of shows the pivotal role of material selection in augmenting neutron flux and overall reactor safety. Additionally, a couple of variations were made in structural design parameters such as the geometric configurations, and this also kind of yielded discernible effects on neutron flux distribution. Optimizing these aspects showcase promising outcomes in mitigation neutron exposure to critical reactor components, thereby enhancing operational safety and longevity. Essentially, the results were quite positive, and I'm sure with a lot more testing and simulation, we could come up with more conclusive and concrete qualitative data. So some of the challenges and that we encountered was of the optimization process was essentially the computational limitations. Despite the power of OpenMC and other simulation tools, the complexity of this fusion reactor system demanded a substantial amount of time and computational resources. Optimizing these blankets requires extensive simulations, and once again, the time constraints has made it very difficult to generate real qualitative data. So, looking ahead, there are exciting avenues for future research and improvement. Advanced simulation techniques, such as perhaps machine learning aided simulations, or even hybrid approaches combining analytical models with computational simulations, can hold a lot of promise for overcoming these current computational limitations. These techniques are a lot more efficient and can produce a lot more accurate predictions, allowing us to explore a broader range of design possibilities. Furthermore, the next phase of this that would be ideal would be to take these from simulations to real world testing. The helium cooled lead lithium blanket has not actually been created yet, but once it has, it can be submitted through extensive real world simulations that can provide very definitive results. Thank you for listening to my presentation. I would like to thank Polygence for allowing me to pursue this kind of research project of mine. And I'd like to thank my mentor, Ms. Soha, for giving me her invaluable guidance in this project. Thank you.